Hi, this is Math 150, Section 2, Lecture 2. So what we're going to do today is we're going to talk a little bit about vectors. We're going to talk a lot about dot product and interpretation of the dot product. How many people have not seen vectors before? Okay, so vectors have a magnitude and a direction. Okay, so this is not a linear algebra class. It would be useful to have linear algebra. As a rule of thumb, if I need material from a previous course or a future course, it's almost always either linear algebra or real analysis. If there is something that is confusing to you or something that you are unaware of, please speak up. Years ago when I was teaching differential equations, I asked the students, we need to do a little bit of 2x2 matrices because otherwise I'm too limited in terms of what I can cover. Is everybody comfortable with 2x2 matrices? And it was a complete silence. And I asked, does anybody want a review of 2x2 matrices? Silence again. I said, okay, well, we have clickers, so I'm not going to report on the results to the class, but I'm just curious, how many of you would like a review of 2x2 matrices? And I asked this with clickers. Okay, so when I asked that question, 43 or 47% of the students wanted a review, but no one was willing to just speak up. I saw some hands going up here, which is great. So almost half the class wanted a review, but was not willing to raise their hand. So the reason I'm telling you this, the moral of the story is, if there's something you want to see, odds are a huge number of people here want to see it as well. Your fellow classmates will thank you, not publicly, but they will be very happy that someone is asking a question. So if there is something that you're unfamiliar with or that you want to see more of, please just speak up. So when we write down vectors, we typically write them in some coordinate system. We often use the Cartesian coordinate system. So in that case, we'll talk about the x-axis, the y-axis, the z-axis, and if we had higher dimensional spaces, we could do that as well. In terms of how we want to denote things, we often use a variety of different notations. Sometimes we'll use I hat for the unit vector in the x direction. And we'll use j hat for the unit vector in the y direction. And we'll use k hat for the unit vector in the z direction. I don't particularly like this notation. It's okay, it's not great. I like to often use I, j, and k for summation variables. But the other thing is, as you add more and more dimensions, what are we going to now do? L, M, N. It starts to get confusing. I like to use E1 for the unit vector in the x direction, or we'll call it the x1 direction, and then E2, et cetera, et cetera, et cetera. In terms of how you want to write vectors, I normally put an arrow over it. The point is I want to be able to look down quickly and see what kind of object am I talking about. Am I talking about a vector? Am I talking about a number? Some books use boldface. Well, for me to do bold on the board is going to be annoying. So I'll just put an arrow on a vector so you can quickly glance down and see what it is. So if I give you V is 3, 4, 5, and W is 8, negative 1, 4, then the way we add vectors is we just add them component-wise. So 3 plus 8 would be 11, 4 minus 1 would be 3, 5 plus 4 would be 9. I use parentheses. Some books use square brackets. Pointy brackets, angular brackets. Doesn't really matter, as long as you're consistent. And so the interpretation is it's a quantity that has both magnitude and direction. So the book gives a lot of examples of physical forces on an object. And maybe you have an object hanging and it's got ropes pulling in different directions and you've got gravity coming down, and then you add up all the vectors to find out what is the net force on the object. So later today we'll prove some formulas involving vectors and dot products. And sadly, a lot of times the only way you can really prove these formulas is to just roll up your sleeves and do a lot of painful algebra. I will try to minimize the painful algebra as much as possible, but sometimes it's needed. Okay, so before we get to the dot product, we need some prerequisite material. So we need the law of cosines. So how many of you remember the law of cosines? Not too many. How many of you remember the Pythagorean formula? We just did that on Friday, so hopefully that should be somewhat fresh. So here is the law of cosines. So if this is a triangle, well, I want to make it clear that this is not a right triangle. So here's A, here's B, here's C, here's the angle. Then we get A squared plus B squared minus 2AB cosine theta is equal to C squared. And then this will allow us to prove the dot product formula. So the dot product formula is that the cosine of the angle between vectors v and w is v dot w over the length of v times the length of w. Right? So we'll prove the cosine formula, and then we'll use that to get an interpretation of the dot product. So let's quickly review what the dot product is. So we take as input for the dot product two vectors, and we spit out a number. And so you always want to ask, what are your inputs, what are your outputs? So if v is v1, v2 through vn, and w is w1, w2, wn, then v dot w is v1 w1 plus vn w1. And this should give you your first result about dot products. V dot w is the same as w dot v. So all I have to do is for each one of these, just because they're real numbers, just write them in the opposite order. And then I'll get w dot v. So that claim isn't too hard to prove. Why do we care about the dot product? Well, it allows us to write some things very nicely. The length of v is the square root of v1 squared plus vn squared. So this is a generalization of Pythagoras. The way you can prove this is, if you have a vector in n-dimensional space, you keep slicing it into small and small dimensions. Another way of saying this is the length of v squared is v1 squared plus v2 squared plus vn squared, which would just be v dot v. So this is our first observation of the utility of the dot product. V dot v is the square of the length. Okay? Now in our dot product formula, here's v, here's w, here's the angle between them. And we're getting v dot w is equal to the length of v, the length of w, the cosine of the angle between them. If I were to switch the order of v and w, what would that do to the angle? If I now would call this one v and this one w, what would be true about the angle? How would it change? The physical angle is the same, but I might now have maybe a minus sign because I'm moving in the other direction. Will it matter for this formula if there's a minus sign in the angle? What kind of function is cosine? So how's the cosine of theta compared to the cosine of minus theta? They're the same. Cosine is an even function. So I actually don't have to worry about whether or not the angle would change by a minus sign if I switch the order of v and w. Because my formula is only going to give me the cosine of theta coming out. And both of those angles would have the same cosine. If I double the length of v, what happens to v dot w? So if I multiply every component of v by 2, what does that do to v dot w? It doubles it. So if we go back to our formula, if I multiply every component of v by 2, this is now multiplied by 2, multiplied by 2, multiplied by 2. If I multiply v by 2, what do I do to the length of v? So if I multiply v by 2, v dot w increases by a factor of 2. What about the length of v? How does that change if we multiply v by 2? It also increases by 2. And if you look, we've got the sum of the squares, and then we square root it. So if we multiply all the components by 2, each of these increases by 4, and then we take the square root, so it's 2. So the two sides are shifted by the same. If I multiply v by 2, the left-hand side increases by a factor of 2, the right-hand side increases by a factor of 2. The cosine of the angle is unchanged because the angle between the vectors doesn't change if I just make v go twice as far. So you always want to get a sense of, is this formula reasonable? And so what kind of smell test, what kind of quick sanity checks can you do on this formula? Well, if I double v, the formula is still true. So I can choose whatever I want for the length of v. What do you think might be a really good choice for the length of v? 1. We might choose v to be unit length. And if we choose v to be unit length, it doesn't really matter, but maybe that's a little bit easier for us to understand. So I'm trying to build intuition for this formula. What direction might you want to choose v to be in? Positive. So let's choose v to be in the positive x direction and see what we get. So this is going to just be a special case. So let's say, assume v is unit vector in the x direction. And so for now, let's just assume we're in two-dimensional space. And then here is my vector w, which will be w1, w2. The dot product is just going to be w1. So in this special case, v dot w is just w1. Now, if we look at v dot w over the length of v, the length of w, this would be w1 over the length of v is 1, and the length of w1 is the square root of w1 squared plus w2 squared. So now we've got w1 over the length of w, which is square root of w1 squared plus w2 squared. What's w1 divided by that? That's just going to be the cosine of the angle. So that will just be the cosine of theta VW. So in the special case when v is in the x direction and it's unit length, then we've seen that v dot w is going to just be the length of v, length of w, times the cosine of the angle between them. So the dot product formula holds in that special case. Did we need to assume v was unit length? No. We've already argued that we can rescale v and the things will still hold. But it is crucial in this picture that v is in the direction of the x-axis. This is where, if you knew linear algebra, you would then say, well, we've proven that it holds when one vector is in the direction of the x-axis. Now let's show that if we apply rotation matrices, that the result will hold in general. That's a more involved proof. It requires you to know some techniques from linear algebra. That's not a prerequisite for this course, so we're not going to do that. But I wanted to give you some intuition that this formula could actually be right. And by looking at a special case, we know that it is at least true in that special case. All right, so now we're going to prove it in general, but to prove it in general, we're going to need the law of cosines. So we come back over here and get the formula for the law of cosines. So it's a squared plus b squared minus 2ab cosine theta is c squared. So we now need to prove the law of cosines. All right. So proof of law of cosines. So here's A, here's B, and here's C. What is the law of cosines generalizing? So it's generalizing the Pythagorean theorem. If the angle is 90 degrees, then you just get a squared plus b squared equals c squared. Okay. What kind of triangles do you think we want? Well, we want the formula to hold for non-right triangles, but as we're trying to do the proof, what type of triangles do you think we want?
Ones with like easy numbers, so that we can do a calculation.
Okay, and so what are the only triangles we can compute with?
Right triangles.
Right triangles.
Okay.
How many of you have ever watched a presidential debate? It really doesn't matter what question a candidate is asked. They meander for a couple of seconds, and then they move into one of their set speeches, right? And it doesn't matter what the question was. Oh, that's a really good question. It reminds me, and then they get to whatever they wanted to say. It's very similar for us. I want to get to a right triangle. I know things about right triangles. You give me a generic triangle, I'm not happy. I want to somehow pass to a right triangle. So I need to generate right triangles from this. So in the 9 a.m. section, we came up with 2 ways to generate right triangles. Any thoughts?
Well, first of all, you can do the line, and it would be like from where angle B is
Okay.
line B.
Okay, so one possibility is to come in like this and draw the altitude and get 2 right triangles. What's another way we could do it? So that's one way. How else could we get right triangles? Yes?
Draw a line down from angle A and expand A out.
So we could expand A out. And now where do we draw the line?
From angle A.
From angle A is over here.
Sorry, angle B.
So the angle between B and C. We could drop this down. Or we could come in like that. Those are the 2 possibilities. Or at least those are 2 possibilities. Any thoughts as to which one we should try? I'm sorry? Doesn't necessarily is it bisect? No, I think it will bisect. When you say bisect, it doesn't imply that it splits in equal parts, right? Okay, so we could try the bisector. So if we do that, we'll call this Y, we'll call this B1, we'll call that B2. And if we did it the other way, maybe we'll call this H, and we'll call this X. So we have 2 different approaches, and we can see which one works. All right, so let's try the bisector first. So bisector. And again, the reason I want to spend so much time on this is I really want to talk about how would you prove, how would you attack, how would you analyze various problems. That's the skill that's going to serve you well in future courses and later in life. Remembering certain specific facts, not as much. So if we try the bisector, we would get a right triangle with A as the hypotenuse. So we'd get A squared would be B1 squared plus Y squared. And in the other triangle, we would get, the hypotenuse now would be C. So we'd get C squared is B2 squared plus Y squared. Okay. All right, so now we somehow need to get something involving B times A times the cosine of the angle. So if we add them together, we could get A squared plus C squared is B1 squared plus B2 squared plus 2y squared. All right, we have an a squared, a c squared. The 2y squared is not great. That needs to vanish by the end of the day. Right? Because the answer should not involve y squared. Okay. What does b1 squared plus b2 squared look like? It looks a lot like the square of something. It's not quite, but what does it look like the square of? Yeah, it looks like the square of b. So we could write this maybe as a squared plus c squared is b squared minus 2b1 b2 plus 2y squared. And now that gets rid of a bunch of things. But now we've got this terrible term b1 b2. This isn't looking pleasant, right? What could I do? Well, I could try to play more algebra with this, or I could temporarily put this on hold. We had two approaches, right? Maybe the other approach will lead to better algebra. And this is one of the hardest things to do, is to basically say, I'm going to just pause this for now and see if another approach is more productive. So for the other approach, what we want to do, is, so we would have A, H, X, C, and B. So we would have, with the big right triangle, B squared is A plus X squared plus H squared. And if we looked at the smaller triangle, we would have C squared is equal to X squared plus H squared. So if we subtract maybe the second one from the first one, we would get B squared minus C squared is A plus X squared minus X squared. And by subtracting, the h's cancel. So now we would get b squared minus c squared is a squared plus 2ax plus x squared minus x squared. So it'd just be that. Okay? So it's looking a lot like what we want. We would have a squared plus b squared minus 2ax equals c squared. Or is this a negative a squared? I think this is a negative a squared. Right? All right, so now we're stuck on that side too. It all comes down to finding one good algebraic substitution to do. There's a lot to be said about this. It's looking a lot like what we want. We wanted a squared plus b squared minus 2ab cosine theta is c squared. We've got a minus a squared plus b squared. We wanted a plus a squared. Okay, not so good. We do have a minus 2ax, but we don't want an x. Right? X is not one of the original quantities for our triangle. How can we replace x? Well, since we have a right triangle, this whole side is just b cosine theta. So x is just b cosine theta minus a. And that's the key substitution. And now we can replace x in terms of the quantities we want. We're going to get a cosine. We'll have a b and an a. We'll have exactly the cross term we want. So we get a minus a squared plus b squared minus 2a, and then x is going to be b cosine theta minus a equals c squared. So now we have a minus and a minus becomes a plus. We get a 2a squared. We have a minus a squared, so that becomes an a squared plus b squared minus 2ab cosine theta is c squared. And so that finishes the proof of the law of cosines. So as a nice exercise, is there a way to make the algebra here work? Maybe I want to subtract, not add. Maybe I want to subtract so that the y squareds cancel, and then try to play a similar game there. You always want to get a sense of how lucky do you need to be in a proof. What's the right way to approach it? What's the way to make the algebra as illuminating as possible? But we now have the result of the law of cosines. So any questions on the law of cosines? Yes?
How did you get the x equals b cosine theta?
So I've got this big right triangle here. And the base of the right triangle is a plus x. And the hypotenuse is b. So by trig, the base is going to be hypotenuse times the cosine of theta. That tells us how much the hypotenuse decreases as we come down. So b cosine theta is this whole thing. This is a, so x must be b cosine theta minus a. Yep. Any other questions on the law of cosines? Okay, so now let's use the law of cosines to prove the dot product formula. So the dot product formula is the cosine of the angle between v and w should just be v dot w over the length of v and length of w. Okay, and hopefully you agree that the law of cosines is probably a good thing to be putting in play, because that does give us a cosine of the angle. Okay, so now let's prove the dot product formula. So proof of dot product formula. So here's v, here's w. What do you think this vector is over here? So what would be this vector? It's w minus v. Excellent. And look at it this way. We go first along v, then we go along this vector, and the net result of that is the same as having just gone in the direction of w. So what plus the vector v equals the vector w? The vector w minus v. So now when I add this and this, the v's cancel, and I just get w. So this has to be the vector w minus v. Here's my angle. And now we can use the law of cosines. So by the law of cosines, and the algebra gets a little bit long, we'll get the length of v squared plus the length of w squared minus 2 length of v, length of w, cosine theta vw is the length of v minus w, w minus v squared. Does it matter if I write w minus v or v minus w if I'm just calculating the length squared? No, they have the same length. They are in opposite directions. If I did v minus w, it'd be going in the opposite direction. Not a big deal. Okay, so now I have this formula. And I want to use this to get that v dot w has this interpretation as the cosine. Do you think I should expand this out as v1 squared plus v2 squared plus dot 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 plus vn squared? Should I use my coordinates? All right, I see several people shaking their head in fear. Okay, why should I not use my coordinates? Do I have coordinates in my final expression? No, I have things like the length of v, length of w, v dot w. I don't want to expand this out. I want to keep this. I want to argue as generally as possible, as long as possible. I'm not trying to do a two-dimensional proof. I'm trying to do a proof that works in any case. So now, if we multiply things out, let's look at the length of w minus v squared. So this would be W minus V dotted with W minus V. And if you're not enjoying the calculation, console yourself with I had to do this twice today and I'm not feeling well. So we've already said that the dot product of a vector with itself is its length squared. Now we want to use the distributive property, and I'll prove that later. That this is the same as W dotted with W minus V dotted with W minus V. And then over here I use the distributive property again, and I'll get W dot W minus V dot W minus, oh sorry, this is W dot V. And the next one is V dot W, and then the minus and the minus becomes plus V dot V. So we'll prove that this is true later. What's the relationship between W dot V and V dot W? They're the same. What's W dot W? I'm sorry? So what would W dot W be?
W squared.
I'm sorry?
W squared.
Not W, almost. W squared would be somehow a vector squared. So you're close. The length of W squared. So we can't really talk about squaring a vector, but we can talk about squaring its length. So this would be the length of W squared plus the length of V squared minus 2 V dot W. And this is supposed to equal V squared plus W squared. And I'm doing the same thing. I'm just being a little shorthand. Length of V squared plus length of W squared minus 2V, length of V, length of W, cosine that. Okay. So this equals the length of V squared plus the length of W squared minus 2 length of V, length of W, cosine theta VW. And now we just start doing massive cancellations. Both sides have a length of V. So since both sides have a length of V, we can cancel. Both sides have a length of W, so we can cancel. Both sides have a negative 2, so we can cancel. And we're left with cosine theta VW is V dot W over the length of V, the length of W, which is what we wanted to show. So it follows from the law of cosines. And nothing we did assumed we lived in a two-dimensional space. When I give you two vectors, as long as the vectors aren't in the same direction, they lie in a unique plane. And so all of this is fine. So now we can talk about interpretations of the dot product. So what's the most natural, what are the good angles we like? I'm sorry? 90 degrees. And so V is perpendicular to W. Does everybody remember this notation from days past in geometry? This means perpendicular. So V is perpendicular to W if and only if V dot W is the zero number. So this gives us a really good, easy test on whether or not two vectors are perpendicular. Just take the dot product. If the dot product is 0, they're perpendicular. If the dot product is not 0, they're not perpendicular. Okay? Any questions on the dot product? Let me just check what was. So if I give you specific vectors now, we can actually check and see if they're perpendicular or not. So if I give you example, V is 4, 3, 1, and W is 2, 6. What do you think I should put in? I think negative 24. Then I would get V dot W is 4 times 2 plus 3 times 6 plus 1 times negative 24. So it's 8 plus 18. Oops, sorry. I don't want 24. What do I want? 26. Minus 26. So v dot w would be 0 in this case. Now, it turns out that, in general, you cannot define an operation which takes two vectors as input and gives you a vector as output. There is a situation where you can do that. It's in three-dimensional space. So if you're in three-dimensional space, there's something called the cross product, which takes two vectors as input and gives you a new vector as output. Because it works in three-dimensional space, it actually works in two-dimensional space as well. All you have to do is, if I have two vectors in the plane, just imagine that their third component is 0. And so you can bump up vectors in a plane to vectors in 3 space. So we'll do the cross product later. So cross product in three-dimensional space. It will be a vector, and we'll denote it, v cross w. And in fact, it's going to be a vector that will be perpendicular to both v and w. Okay. So what I want to do now, well, I don't want to do it, but I think I should, is I want to show you why the distributive property holds. And this is just one of those situations where you just have to roll up your sleeves. Most of the vector identities follow similarly. It's just a matter of patience. And frequently, the best way to prove things is to write things down in your coordinate system. All right. So this will be the proof of the distributive law. So let's imagine we have A dot B plus C. And now let's just go through the algebra. All right, so this would be A1, AN, dotted with B1 plus C1 all the way down to Bn plus Cn. All right, well, now it's the dot product of two vectors. So it'll just be A1, B1 plus C1, plus A2, B2 plus C2, plus dot 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 AN, Bn plus Cn. Okay. Well, we can just do the multiplication out, and this will be A1, B1 plus A1, C1, all the way down to AN, Bn plus AN, Cn. And now, how do you think we should group things?
Like the A1s with the B1s and the C1s and the ANs with the BNs and the CNs.
Okay, so you're close. How should I group it? So what's the first term I should write down? Say A1, B1. What term should I write second? Yes? A2, B2. I'm sorry?
Where's the A2?
Well, I have all the different terms. I have A1, B1 plus A1, C1 plus A2, B2 plus A2, C2 plus A3, B3 plus... Wait, let's put all the AB terms first and all the AC terms second. So I'll end with AN, BN, and now I'll have A1, C1 all the way down to AN, CN. And now, what is the first n terms? What does this equal? So what would this be? A1, B1 plus A2, B2. Yeah, that'll just be A dot B. And similarly, the next term will just be A dot C. And that finishes the proof. So this proves that the distributive law holds. A dot B plus C is A dot B plus A dot C. If I want to multiply V dot W, if I multiply V by 5, I'll change the dot product by 5. You can go through and just prove all these results hold by just doing the algebra. Okay? It's not necessarily exciting algebra. How many times in your life do you have to do this algebra? Once. Unless you're teaching multivariable calculus, in which case then you have to do it multiple times. And, I'm almost on enough medication that I don't really mind doing it twice today. Almost. It's not fun. Okay? And then you can have more complicated formulas involving the dot product and the cross product together. Sometimes you can step up to a higher level and give a geometric interpretation for what you're doing and actually bypass a lot of the brute force algebra. I'll talk a little bit about some of that at later dates when things work out nicely. But, all right, so are we comfortable with arguments such as this? Okay, I want to now go back and just do one last little bit from I'm not quite sure how far back you have to go into your elementary school days for the area of a triangle. But my daughter, she's in 3rd grade. She had to do this. If I give you a triangle like this, so here's the base, and here's the height. The area of a triangle is 1/2 base times height. Right? We proved the area of a right triangle was 1/2 base times height. And the way we did that was we took our square, we divided the square in half, and said the two triangles are similar, so each one has to be half the total area. How many of you remember how to prove the area of this triangle is also 1/2 base times height?
Well, from that, you can make it an entire rectangle. And then, you know that...
Okay, so we could try to make it a rectangle. And then what would we do once we make it a rectangle?
Well, and you can see that you're splitting it in half. And then that means that the triangle with B would be similar to the other triangle on the other side, and then
Right.
the triangle with H would be similar to the triangle on this side as well. So it would still be 1/2.
You're close, but not quite. Yes?
Can we use the bisector method and create 2 squares?
Can we use what?
The bisector method and create 2 squares?
How would we create two squares or 2 rectangles?
2 squares by like the right angle, or like bisecting the triangle into 2 right triangles.
Okay, so coming up like this. So if we come up like this, the only problem is we're not using this height. And now we're making this the base.
If you use the
So I'm not saying it doesn't work. But we want to use this height and that base. Yes?
Can you draw another height and base and have it inside a rectangle, and then you would have 2 right triangles?
We already have 2 right triangles. There's 2 right triangles in this picture. Here's one right triangle down here. Right? Let's call that side X. So we have a small right triangle, and we have a big right triangle. So for each of those right triangles, we already know the area. And then if we subtract, we'll be left with the area of this one. So area of the whole is just going to be 1/2. What's the base of the whole thing? B plus x. 1/2 b plus x times the height. And then the area of the small triangle will be 1/2 xh. And so if we subtract the area of the original triangle, will just be 1/2 bh, because the 1/2 xh cancels with the 1/2 xh. So again, I'm not saying that the other suggestions that were thrown out won't work. it's a good idea to try and see if you can make them work. This goes back to, think presidential debates. I like right triangles. I want to try to get as many right triangles in play as possible. Which right triangles do I want? And so, again, it's absolutely defensible to say I want this right triangle coming in like this. The problem is it doesn't allow me to use the height that I know here. And that's why I prefer using this triangle coming down like that. So this is very similar to a proof of law of cosines. Whenever you see something occurring multiple times, you begin to think this is a technique, this is important, this is something you should add to your toolbox. You want to find ways to make the algebra work out nicely. Okay. Any other questions on proofs of areas of triangles? Again, it's often difficult to remember exactly what have you proven when it's been done so many years ago. Does anybody actually remember proving this formula? I don't. I know my daughter, she's in 3rd grade, I know they were doing that on their homework this week, although this was the challenge math homework for her. So it might be 4th grade and not 3rd grade. But just how do you figure out which things to look at? That's really challenging. Okay, I think I have covered the questions and comments people wanted. Any other questions? Any other material? Okay, so we'll continue on Wednesday with the next set. And then if you haven't handed in homework, please do so.